there is this cylinder, sorry, sphere, spherical tank. Right, so spherical tank, and there was ice inside. Ice water. 0 degree, 2 meters, and outside the air or the surface outside is 20 degree, and epsilon for both surfaces. Did you call it 1 and 2? Something. Epsilon is 0.15. Right? And the geometry here are such that this is 1.5 centimeter, and the thickness is 0.5 of the first tank, inner tank, and then 0.5. Right? So each wall is 0.5 centimeter and 1.5 centimeter thick airspace. So actually in the sketch they show vacuum, and in the problem they say air. Either way, we will just assume that when it has to do with radiation, air is just transparent for radiation. He will not really block or do anything. Thick airspace between the two walls of the tank evacuated in order to minimize heat transfer. Okay, so he took the air, and there is vacuum in there. Alright. And the surfaces are polished, so it's really shiny, so that each surface has a luminosity of 0.15. The temperature of outer wall is 20. Assume the inner wall to be at 0. Determine the rate of heat transfer to the ice water. So require Q dot 12 and the amount of ice at 0 that melt during the 24-hour period. M dot ice. So again, I can go with this scenario where I would imagine sigma T1 to power 4, sigma T2 to power 4, and here's 1 minus epsilon 1 over area 1 epsilon 1, and 1 minus epsilon 2 area epsilon 2, and 1 over f area 1 f1 2. Or I could just open that table for two spheres basically radiating to each other, and I find immediately the equation Q dot 12 is area 1 sigma T1 to power 4 minus T2 T1, and it's 1 minus epsilon 1 plus 1 minus epsilon 2 over epsilon 2 d1 over d2 to power 2, and where 1 is actually the inside and 2 is outside. And that's the issue. This is 1 and this is 2. Right? So this is the equation that we will use. So do we know T1? Yes. So that's the 0 plus 273, because it needs to be in Kelvin. All the temperature should be in Kelvin.
Not 0.
So T1 is the inner surface. The inner is at 0.
Yeah, it's not 0 Kelvin. I see. Yeah.
Right, so the T in here need to be in Kelvin, and he is telling, right, the T in this T to power 4 should always be in Kelvin, and he said the ice is sitting at 0 degree. So it's 0 plus 273, and T2 is the 20 plus the 273. All right, and the area of the sphere is, what's the area of the sphere? 4 pi r square or by d square. right? Pi d1 square. So that's pi multiplied by what's the diameter? No?
0.00.
So it's 2 meter. That's the in the drawing. If you look at the drawing, it's actually 2 was the inner surface, and then there is a thickness of the. So if the 2 finished here, and then there was this shell, and that shell was 0.5 centimeter. That's the. This is 1.5, and then another 0.5 here. So again, how much is D1? 2.01, because there is 0.5 here, and there is 0.5 on the other side. The thickness of the wall is 0.5 centimeter on one edge and 0.5 on the other edge. So 0.5 centimeter, 0.5 centimeter, that's 1 centimeter. So the diameter in the inner surface is not 2, that's the inner diameter. The diameter is actually 2.01. Alright. And so D1 is 2.01, and D2 would be, how much is D2? So again, 2 meter is the inner diameter of the inner. In that sketch, if you look at the sketch, let me show you the sketch for a second. So it's pretty clear that 2 is the inner diameter. The surface that's radiating is this. That's the one radiating to this line. So those are the diameter that we care about. Right? This is the surface that's radiating, that's D1. And D1 is not 2 meter, it's Q1. And D2, that is the surface that is radiating to, it's not really this guy, right? That's convecting to the outside. But it's this that's radiating to this ground. So this would be 2 meter plus 0.5, 1.5, 0.5. So that's 2 centimeter here, 2 centimeters there. So it is 2.04. 2.04, and for our online friends, that's the sketch. And so you can see how the inner diameter was 2 meter in that place. All right. So anything else? We know epsilon 1 and epsilon 2, of course, and so we just calculate the Q as 107 watts. All right. Now the second part. He asked about how much ice will melt, the kilogram per second. So how can you calculate this? Let's see. So the heat that is going by radiation, yes, is going to the ice and it's going to increase the energy of the ice. But because the ice, it's ice water. I mean, it's ice and water. He will not change his delta T. He's not going to move from 0 until what happens? We are giving him all the joules. And he's supposed to heat up, right? But no, it will not happen. He will not increase his temperature until all the ice melts, right? And so all this happen at 0 C, 0 degree C. So the Q dot is not m dot CB delta T. That's if the delta T will change. But the Q dot should be m dot multiplied by the fusion heat rate, or basically HIF. How much energy does it take for this thing to melt? Right? And we solved a bunch of problems like this before in our book, right? And so this 107 watt will be m dot multiplied by, that thing was 33 kilojoule per kilogram. Right? That's 33 kilojoule per kilogram. I think it's, that's a good place, right? In front of the book. But we solved a problem about exactly the same thing before. Which table is it that has the latent?
I think it's on 869. Let me look.
Which page?
I think it's
869.
869. No, 867.
867, latent heat of fusion. Can I see?
On the bottom.
Yes. So on page 867, you can actually, so this table shows us the latent heat of fusion, HIF, how much it would take to melt 1 kilogram. And so for water at 0 degree, 333 kg per kilogram. Thank you. Right, so 107 watts will give us the, so this is 107 watt and this is kilojoule per kilogram, so we actually need to divide this, multiply by 10 to the power 3, so that become joule per kilogram, and this will actually give us, what's m dot? What's the unit of m dot? This would be kilogram per second, right? But when you read the problem, he actually said the amount of ice that melt during 24 hours. So this is what will happen in every second. Every second, this much kilogram will melt. So in 24 hours, how can I get the m in 24 hours?
Times 3600 times
Right.
24.
So I multiply this number. So this number times 24 times 3600. That's how many seconds? That's how many seconds we have in 24 hours. And so eventually, what is this number? 27.8 kilogram. This is how much ice will melt. Or basically those joules that you end up transferring in 24 hours will end up melting this much ice. Right? Question about this?